All right, welcome to this session on what's new for BLU in DB2 11. And as most of you know, DB2 11 came out earlier this year, and there are a number of very significant enhancements for BLU in that release. So we're going to talk about those here. I am aware that there have been a number of other sessions already in the last 2 days that talked about some of those enhancements for BLU in version 11. So some of this material may seem familiar, but maybe that's okay. And please do feel free to ask me additional questions, right? If there's anything you want to know beyond the slides, the more interactively we can do that, the better. All right, so the agenda for my presentation is that I'll start with a brief overview to point to a few highlights for BLU in DB2 11. And after that, we'll go into some of the technical details. Of course, we talk about BLU in DPF. And then I want to spend some time to talk about the query performance enhancements for BLU in version 11 that apply for DPF and non-DPF. And then there are a number of other really useful enhancements for BLU as well that I also want to talk about towards the end of the presentation. Okay. Let me skip over this. All right, if we wanted to summarize the most important enhancements for BLU in version 11 on one slide, then it could look like this. So this gives you the one-page overview of what's new for BLU in DB2 version 11. And of course, the big new thing is the BLU support in DPF. We also call it BLU MPP, and we'll talk about that in a fair amount of detail. And then we have a number of enhancements for query performance. For example, we have a native implementation for sort so that we can sort directly on the compressed columnar format that BLU has. And I'll explain why and when that gives you a significant performance benefit. Along with that, we have optimizations for OLAP functions to also evaluate many of the common OLAP functions directly on the columnar format of the BLU data. We have an additional join method for BLU, a nested loop join, which is optimized for BLU. And again, I'll show you examples where and for which type of queries that join type is beneficial. There were some enhancements to merge in BLU as well. And then from version 11 onwards, it is possible to have declared global temp tables as column organized tables. That was not possible before. And it's also now possible to have parallelized inserts into these column organized declared temp tables. And such temp tables, for example, are used by reporting tools. MicroStrategy, for example, is using them a lot. And then a few restrictions were lifted, which are very important. So for example, now in version 11, you can have identity columns in BLU tables. You can have generated columns in BLU tables, very important features, of course. For security, the row and column access control has been enabled for BLU, so that is available now as well. And some enhancements to better help you deal with local languages. So the situation was that in DB2 10.5, you could use BLU only if the database code page was Unicode. Otherwise, BLU was not possible. Now in version 11, we also allow BLU in a database with code page 819. That was the code page that most customers had requested. You can alter BLU tables now to make them not locked initially. You can have wide rows. We have optimized even more scalar functions in DB2 for BLU. There also have been some enhancements to rewrite in the compiler to get better execution plans for certain types of queries in BLU. And there has been some amount of work to improve the sort heap usage in BLU. Now that's actually a very important part, and I'm not going to talk about that much later. So as you might know, BLU is using the sort heap much more aggressively than DB2 with row-based tables, right? A lot of sort heap is needed for hash joins, for aggregations, and so on. And it is not always easy at runtime to estimate how much a sort heap will be used by this hash join or by that hash join, right? And so there had been situations when we were reserving maybe too much sort heap for a certain operation or not enough sort heap for a certain operations, which is obviously not good. And there have been improvements to make that utilization of the sort heap more efficient, more precise. All right, so that's BLU in version 11 on one slide. Now, before we go into technical details, I want to point out a couple of performance results. We did some tests with BLU on a single server, so non-DPF, and we used a multi-user warehousing workload, and we ran this on Db2 10.5, fixspec 5, and Db2 11, and we measured the throughput, so how many complex queries can be executed per hour. And we found that in version 11, the throughput was roughly 1/3 higher than in version 10.5. So that's a very positive performance result, of course, but it's interesting to look under the covers at the queries. What exactly did they benefit from? And the investigation showed that some of the queries in the workload were faster because of the native sort and the native OLAP implementation. And I'll show you some examples later to explain why that makes the queries faster. Some queries have benefited from better execution plans and rewrites. And overall, the multi-user throughput has also benefit from the improved utilization of the sort heap. You can imagine if you have many concurrent users all competing for sort heap, it's important that each user allocates only as much sort heap as they really need, right, internally in Db2. And then for BLU on DPF, I want to talk about not so much about the absolute performance, but more about scalability. Because if you run a complex workload in a cluster, right, in a system where you have multiple nodes and you can scale horizontally, then really what you want to make sure is that the system, the architecture, can give you a linear or near linear scalability. And there are two ways, or at least two ways, to look at scalability. And the first one is what I want to discuss with the picture on the left, and that's if I have a fixed workload and a fixed volume of data, and I increase my computing resources, let's say I add nodes to my DPF cluster, is the performance going to increase linearly with the increase in hardware? So what we tested was a DPF system with 3 servers, 6 Db2 partitions, and 10 terabytes of raw data. And then we doubled the size of that cluster to 6 servers, 12 database partitions, but still the same 10 terabytes of data, the same workload. So we doubled the resources, and we saw that the throughput improved by a factor of 1.9 roughly. So that's not the perfect scalability. You know, we are doubling the resources and the performance goes up by 1.9. So that's near linear scalability, not so bad. It's a very nice result. The other way to look at scalability is here on the right-hand side, and that's really if you are asking what happens if my data volume grows. if I have more data, can I keep performance constant by adding more resources, more hardware resources? So what we did in this test, it's almost the same test as on the left, but when we doubled the DPF system from 3 nodes to 6 nodes, we also doubled the data volume from 10 terabyte to 20 terabyte. So double the data volume, double the hardware, and we found that performance is approximately the same, which again is an indication for near linear scalability. So this was really important also for us internally to understand and to verify that BLU DPF implementation works well. Any questions so far? Just one question. On Z-Linux, I don't think so. On Intel platform, not in my slide deck, but we may have something, results that I don't have here in my presentation. So for the recording, the question was about, do we have results on other platform than Power?
I know it already works well on Power PC and AI. What about other platforms?
Okay. Okay, so let's look at BLU in DPF. I assume that most of you are familiar with a DPF, the concept where a database is partitioned, and the database partitions can be spread over multiple servers, so you have horizontal scale out, and so far that was not possible with BLU. Now in version 11 that is supported with BLU. I think the two key benefits is that first you can manage much larger data volumes than you could reasonably do with a single server. And the other benefit is by having this horizontal scale out, you can parallelize your queries across the database partitions, and that further helps you to reduce the response time of the complex queries over large data volumes. Okay. So when you start thinking about BLU in DPF, one of the first questions that comes up, okay, how about capacity planning? How about sizing? How do we configure the system? Is that the same as before? What do we need to know here? And the answer is that the BLU sizing guideline at a high level is very similar for DPF and non-DPF. And the rough rule of thumb is that we recommend 8 CPU cores and 64 gigabyte of main memory per 3 terabyte of uncompressed raw data. And that's just a very rough recommendation. Of course, if you have more knowledge about your workload, if you know about hot data, cold data, etc., then you can do the sizing more accurately. Of course, more CPUs, more memory is always helpful, especially if you have many concurrent users. I said that the BLU is very hungry for sort heap, so if you have a high degree of concurrency to support, then certainly more memory is recommended. Now, if you have an existing DPF system and you want to start using BLU, and you find that in your existing system you don't have that many cores or that much memory to match the recommendation that you see here, then that doesn't necessarily mean that you cannot start using BLU. It just means that you need to be a bit more careful. You want to check the configuration of the buffer pools of the sort heap. You may need to reduce the buffer pool, increase the size of your shared sort heap in order to make the system work well for BLU. To help you with the system configuration, we have this registry variable db2 underscore workload that you can set to analytics. For example, if you do that before you define a new database, then the database will automatically pick certain configuration parameters to give you a good starting configuration for BLU. And we already had that for single server BLU in version 10.5, and that has been extended for DPF. So it will give you appropriate values, for example, for the number of FCM buffers, FCM parallelism, based on the number of partitions that you have, and so on. And then, of course, another important question is, let's say we are designing a new DPF system, how many partitions, right? How many partitions per server? What should be the ratio of CPU cores per database partition? Does that change with BLU at all? So here, in this example, I'm looking at 3 servers, each have 24 cores, and well, you know, I have different options. I could put just one big partition per server, or maybe use very small partitions. You know, in the with row-based tables for a long time, it has been fairly common to have a large number of smaller partitions, like indicated down here, that would give you, for example, 1 or 2 CPU cores per partition. And the reason for that was typically because the query parallelism within a partition was not very good. But if you have many database partitions, then the query can be parallelized across the partitions. So many partitions means lots of parallelism and better performance for your queries. But this is something that is a lot less relevant for BLU, because the SMP parallelism for BLU is a whole new implementation that we did in 10.5. So the BLU queries parallelize even within each partition really, really, really well. So just for that reason, you don't need to have many small partitions, right? And you also need to keep in mind that a large number of partitions can have potential drawbacks. For example, the network communication between those partitions. Imagine a query where maybe the content of one table needs to be shipped to all of the other partitions. Then the impact on the network is linear in the number of partitions that you have. The more partitions, the more network activity. So fewer partitions can reduce the load of the DPF network, which is really helpful for performance. So you may need to make that decision based on what your needs are. There are certainly also operations where many partitions are helpful. For example, backups, right? Backups in DPF can be parallelized across the partitions. So if you have very large backups that you run, and if you need to make sure the backup completes within a certain time window, then you still need a certain number of partitions to have enough parallelism for your backup. But if you're building a new system, then as a rough rule of thumb, I would say a medium design is usually good for most requirements. So roughly 1 partition per CPU socket is something that I would use for a new DPF configuration with BLU. Again, if you have an existing system where you have a larger number of smaller partitions, you can still use BLU, right? It will work, you will see performance benefits, but if you're building a new system, then you may want to take these things into account. Okay, so the data distribution in DPF works for BLU the same as it used to work for row-based tables. You can specify a distribution key for your tables, and then the data will be hashed on that key across the database partitions. And the guidelines for picking a distribution key are the same as for row-based tables. You know, pick a column that has a large number of distinct values. A primary key, for example, is a good distribution key. And if you can, look at the big joins that need to be executed frequently. If you have tables that need to be joined very often, then using the join key as the distribution key means that the joins can be done locally within each partition without having to ship data across the partitions. That's a question.
For the CPU and memory recommendation, for a single system, you recommend 8 CPU, 64 memory. What about for partition-based system? Do you recommend each node has at least that amount of resources, or it doesn't matter for partition?
I'm not saying that each partition should have at least that, but probably each server in your cluster should have that. I mean, it would be hard these days to have a server with less than 8 CPU cores, right? Yes, the system as a whole should follow that same guideline. Okay. There is a new option in version 11 for DPF where you can distribute data in a DPF system by saying in the table definition, distribute by random. And this is really an option for situations where you have no knowledge about your tables, no knowledge about the data that goes in and how that data will be used. Okay? Because if you know nothing about that, then, and you just pick a column as a distribution key, you may pick a bad column and the data may get very unevenly distributed across the partitions, and that's obviously bad for performance. So with the distribute by random, you are at least guaranteed that every partition has approximately the same amount of data for this table, which is good. The distribute by random clause will never give you co-located joins. But I mean, if you know nothing about how your tables will be used, if you don't know the workload, then it's not possible to pick distribution keys for co-located joins anyway. But if you do have knowledge about the workload, about the data, what are the join keys, then absolutely it's better to pick distribution keys by hand to improve the joins. Okay, let me skip over the co-located joins things. Okay, compression. So compression continues to be very important for BLU, and with BLU in DPF, compression follows many of the same concepts as before. That is, in a BLU table, there's a separate compression dictionary for every column in the table. And the compression is important not just to save space, but also for the query performance. The more the columns are compressed, the better the query performance. If columns or tables are poorly compressed, the query performance will suffer. So the compression is really, really important for BLU. And one design decision for BLU DPF was that for a table that is distributed over database partitions, the compression dictionaries are the same on every partition and available locally in each partition. Of course, it's important that the compression dictionaries are available locally in the partition for fast access for performance. And the fact that they are identical across the partition means that if data needs to be shipped from one partition to the other, it can remain in the compressed format because it can still be interpreted on the other partition because there we have the same compression dictionary. Okay? And if we are shipping compressed data over the network, well, that's a lot more efficient than sending uncompressed data, right? And that's a big difference to the behavior of traditional row-organized tables in BLU. So keeping the data compressed across partitions is very important. So how does it work if you have defined a new table and you start pushing data into your new table? Well, let's say the table is distributed across these partitions here. Then each of the partitions participate in analyzing the data to build histograms, etc., to get the information that we need internally to build a compression dictionary. And then one partition is automatically selected to collect the histograms from the other partitions, to combine that information, to build the compression dictionaries, one for each column in the table. And then those compression dictionaries are copied out to the other partitions so that every partition has the same dictionaries for that table. So every partition where the table is allocated has the compression dictionaries. Now, let's look at another example. Let's say I have my table T1. Let's say it's a small table, and I have decided to allocate it on only one partition right here. And that is the dictionary for my table T1. That dictionary is only available on this one partition where table T1 is allocated. So T1 is a non-partitioned table in this case. And table T2 is partitioned across these partitions here. And you see the dictionary is available on each of the partitions. Now, what happens if I need to do a join between these two tables? Well, the data of table T1 probably needs to be shipped to the other partitions to perform the join with T2. But since the other partitions don't have a compression dictionary for T1, the data in T1 needs to be decompressed before shipping it over, which is not optimal, right? Also, if the T1 data is being decompressed before the join, then the T2 data also needs to be decompressed to do that join. So we may be decompressing a lot of data and then do that join on uncompressed format. That is not ideal for performance, right? So opposite to what you may have done with small tables in DPF in the past, you may want to consider distributing even your small tables. So at the bottom here, I hope you can see that from the back, I have decided to define table T1 as a distributed table. It's hash partitioned across the same partitions as T2, right? It may not be a co-located join, but still now the compression dictionary of T1 is available on each of the partitions. That means the join between T1 and T2 can be done on the compressed BLU format, a much more efficient way to perform that join. And we've seen examples where this can make a really, really significant difference for the performance. We have a question. Can you replicate BLU tables? A good question, because when you look at this picture, what comes to mind is I make table T1 a replicate to tables, and then I have this problem solved, right? Well, not quite. Even though it can be replicated, as far as I know, the replicated table will not be compressed either. It's a limitation right now, so no, unfortunately, that doesn't help. I mean, I think we all need to get more experiences with small tables in BLU DPF. So far, the indication is that distributing the small tables is a good thing. And in the past, when you had replicated to tables, or you put small tables as non-partition tables. You really did that not from a logical database design point of view, but really to work around performance bottlenecks in DPF, right? And it'd be nice to not have to worry about this anymore. If it could be really simple to say every table gets partitioned across all partitions and be done with it, no special casing for small or medium tables, that'd be very nice, right? So I hope that that's where we can get. Okay. So I think I mentioned most of the things that are here. Oh, maybe one more thing, the redistribute. So redistribute, as you know, is kind of a painful thing to do. Ideally, you don't have to do redistribute. But with BLU, just so you know, this redistribute option, not roll forward recoverable, is not supported with column organized tables at the moment. That's just something to keep in mind. Okay. All right. So far for DPF. Any questions on DPF before I move on? Yeah. One more question. Yeah. The question is, if a replicated MQT in DPF is not compressed, does that mean that replication with HADR also does not compress the replicated tables on the other side? No, that's not the right conclusion. If you use BLU in an HADR pair, then certainly the tables on the standby are fully compressed as they are on the primary. The way HADR works is very different than replicated MQTs in DPF. So HADR works just fine. Okay, other performance enhancement, which are also applicable to non-DPF, because we know BLU is also very powerful and very popular in non-DPF installations. So the first I want to talk about is a native sort and OLAP implementation. And the background is that previously in DB2 10.5, the situation was that when a query is executed and at some point a sort is necessary or an OLAP function needs to be evaluated, then DB2 internally has converted the data from the compressed columnar format to its traditional row organized format and then performed the sort or the OLAP function evaluation. And that's not necessarily bad. For example, there are many queries where you just have an order by at the end to sort the result set before the result set is being returned to the application, right? But the result set is being converted to row format anyway, so doing that conversion and then the sort is just fine. However, there can be cases where it's not so good. And I have an example here on the right-hand side where you see this is a query with a common table expression, V1. And the common table expression includes an OLAP function, a sort operation right here. And then this common table expression is being used down here in the main block of the query. And then there are additional joins and additional aggregations on top of this common table expression. So such a query in DB2 10.5 would require conversion internally on the fly, conversion from the columnar BLU format to uncompressed row organized format already here when the OLAP and order by gets evaluated. And that means all the subsequent operations are also executed on uncompressed row organized format, no longer exploiting the benefits of BLU. And in that situation, the performance is really suboptimal. And let me show you an execution plan to explain that better. So here's an execution plan, the way it might have looked with DB2 10.5. You see there are a couple of sort operators in the execution plan here in bright green. And we read the execution plan from the bottom to the top. And before the first sort is executed, you see the CTQ operator here. That's the columnar table queue, which converts data from the columnar BLU format to the traditional row organized format. And then the sort would be done. And then everything after that, so another join, another sort, etc., would all be done in the traditional row-oriented DB2 runtime. So whatever happens below the CTQ is in the BLU runtime with all the BLU optimizations. Everything above the CTQ does not use the BLU optimization anymore. So not the most efficient execution plan. With the new sort implementation that can sort compressed columnar data directly, well, we don't need this conversion to row format anymore to do the sort. So in DB2 11, the execution plan for the same query would look like this, as you see here on the right-hand side. You see the CTQ has bobbled all the way to the top, meaning the two sort operations, all of the joins can all operate on the BLU data format. Much, much better performance for this type of query than in version 10.5. Now, I said we have this optimization for sort and also for OLAP functions. Now, this optimization for OLAP function applies to the most commonly used OLAP functions, not to any OLAP functions that's possibly supported in the SQL standard. Functionally, all of them are supported, they will run, but this performance optimization applies to those that we have seen customers used most frequently, like rank, dense rank, row number, first value, the typical aggregation functions, and so on. And as you might know, OLAP function have an optional windowing clause, and the windows over which to compute these functions can be specified in terms of a range of rows or a range of values. And this optimization that I'm talking about here is, it kicks in for windowing specifications that specify the window in terms of rows. So for example, rows between unbounded preceding and current row. If you specify a window in terms of a range of values, that optimization would not kick in. Okay. All right. Nested loop joins. Okay, so the background is in BLU in version 10.5, every join is a hash join, and that's good and appropriate for most joins that you want to do. The limitation is that hash joins really only work for joins with an equality predicate, right? If you have joins with, let's say, a greater than or a less than, or if you have joins with some complex expressions in the join predicate, then a hash join cannot really be used anymore in BLU. Then the typical join method would be a nested loop join. And the way it worked in 10.5 is that when such a join would have to be computed, DB2 would again use that CTQ operator in the execution plan, convert the data to row organized format on the fly, and then use its traditional nested loop join for row organized tables. That works, but not always as efficiently as you might want. So now we have a native nested loop join implementation that works directly on the compressed columnar data with many of the same benefits that I just talked about. And we have an example here, one query where you see the join predicate in red. It's a greater than and a less than for this join. And in DB2 10.5, what the execution plan would show is that that nested loop join that needs to happen here has two input legs, and both of these legs would have a CTQ operator to convert both sides of the join to row organized format and then do the nested loop join in the traditional row oriented manner. Of course, that means you are not using the BLU optimizations anymore at this point. And if you look at the details of the execution plan, for example, here, this number above the CTQ operator indicates that 120 million rows are being converted from column format to row format. That's a lot of conversion, right? Not optimal, not even close. So we want to do this nested loop join now in 11 natively on the row format so that we don't need to use the CTQ for conversion here. This is what it would look like in DB2 11. You see that the CTQ operator again has bubbled all the way to the top. Everything underneath is happening in the BLU runtime as efficient as possible. The nested loop join here is now a native BLU nested loop join, a lot more efficient. So there are a certain class of join queries that benefit from this enhancement. Okay. Oops. Okay. All right. Some other BLU improvements that we should talk about. Wide rows. You may recall that I believe in 10.5 or so we have introduced a feature for row organized tables called extended row size, where you can declare tables that are wider than the page size. And now the same is possible for BLU, though the implementation internally is a little bit different. So what we mean by wide rows is, let's say you have a table space with 32K pages, and if you were to define a table with 3 varchar columns, all of them varchar 16,000, then before DB2 11 with BLU, this would fail. Now this is possible. So for row organized tables, if you declare a table like this with the extended row size feature, what would happen is when you insert a row where the sum of the varchar values is larger than your page size, the DB2 would internally allocate a lob to overflow the data into a large object. With BLU, this large object method is not necessary, which is very nice actually, because in BLU, each column is on a separate set of pages anyway, right? And our recommendation for BLU is 32K pages, and that means each column value can be up to 32K roughly, okay? So we can accommodate those values easily in BLU. So that's very nice, so that you can define those wider tables, and large page size for that is recommended. I mentioned at the beginning, declared global temp tables can now be column organized. And here you see an example. If you declare a global session table, you can define this as organized by column. If you are using an MPP system, then You can also declare that to be distributed by hash across the partitions. And this is really useful. For example, reporting tools or sometimes ETL processes use such declared global temp tables to store intermediate results. So they would do an insert from subselect into the temp table, and then they might have another insert from subselect reading out of this temp table, inserting into the next temp table, and so on until they arrive at the final result that they want. And if your base tables are already blue, are already column organized, then it really helps performance if the declared temp tables are also column organized. That's the big win here. Okay. And all of the different options like logged, not logged, etc. for DGTTs are supported, except this one combination, which is not logged on rollback preserved rows. So this is the one combination of options that is not allowed for column organized declared global temp tables. All right, what else do we have? Yeah, so the inserts into such a column organized temp table can now be parallelized, which is really important for performance. Now, the subselect of such an insert from subselect would certainly always be parallelized in blue, right? But then it all used to get funneled into one thread that does the insert, and then that's the bottleneck. But now the insert itself is also multi-threaded to do parallel inserts into such a temp table. And that really makes a big, big difference for performance, and we've done a number of performance measurements on that. And what you see here is the performance of such an insert from subselect with 100 million rows, so fairly large amount of data. And you see the elapsed time relative to the degree of parallelism that was used. So this is the elapsed time with no parallelism in Db2 10.5. This is the elapsed time, for example, with SMP parallelism degree 4, and we see the elapsed time is about 3.8 times faster. With parallelism degree 8, the elapsed time is about 7.4 times faster than no parallelism, and so on. So very substantial performance gains. And we hope to have the same parallelization soon also for permanent for permanent blue tables, for regular column organized tables. Okay, so scalar functions. Even in 10.5, we have optimized many of the most commonly used scalar functions for blue, meaning that the scalar functions can be evaluated directly on the compressed column organized format in the blue engine. But in 10.5, we hadn't done that for all scalar functions. So now we have addressed another set of scalar functions to optimize them, or in some cases to re-implement this scalar functions for native execution on the blue data format. So in 10.5, if you had queries that maybe used LPAT, RPAT, or log or mod and so on, you might have seen that the execution plan, the performance was not as optimal. That looks a lot better now for this additional set of scalar functions. Okay, so this is pretty much everything I wanted to talk about. So here I'm back to my summary slide that I had in the beginning with a list of the key new blue features in version 11. All the items that are shown in blue here, no pun intended. The blue items were the ones that we discussed in the sessions. The black one we haven't discussed, but you'll find documentation in the Knowledge Center, so you can go out there and have a look. And we have a few more minutes for questions, if there are more questions. There's one more question here. How does the access plan work with common table expressions as opposed to DGTTs? Well, we have done a number of optimizations for common table expressions as well, so that they don't have to be evaluated repeatedly for BLU. So at a high level, it should work well. If you get into very complicated queries, then you may need to see which one would work better for you. Are you specifically referring, for example, to MicroStrategy?
No, I'm not. Just wondering in 10.5 will it be below the CTQ operation?
No, the evaluation of the common table expressions would happen in the BLU runtime. It would happen typically below the CTQ operator. So the fact that there is a common table expression, that itself would not be a reason for us to convert the data to row organized format. Any other questions? All right, thank you very much.